Hello everyone. My name is Priya Shaji, and I work as a data scientist at Memorial Sloan Kettering Cancer Center, and I work with applied data science team in strategy and innovation department. As a short bio, I completed my master's in data science from CUNY School of Professional Studies, followed by an internship in NYC Office of Technology and Innovation. So at MSK, we help clinicians make their work easier in clinical care and also fill clinical and operational gaps in care, and hence improve overall clinician and patient experience. One of the problems that our clinicians face is reading through patients' notes, which are pretty long and can take up to an hour, especially in an inpatient setting. So, in our specific use case, we had clinicians reach out who treat patients who underwent a bone marrow transplant procedure or a BMT procedure. Now, a BMT patient have lots of notes before, during, and after their procedure or their transplant, and it's pretty time consuming for clinicians to read through all of their notes. And one of the most common symptoms that a BMT patient experiences is diarrhea. And since their notes have mentions of diarrhea in them, it's not efficient for a clinician to remember extracts or incidents of diarrhea or each and every occurrence of the term diarrhea throughout the patient's notes. So, why are we looking for diarrhea incidents? And the reason we can't miss the occurrence of diarrhea in notes is because if there is any mention of diarrhea, patient might be experiencing what is called as graft versus host. Graft versus host is when the patient is rejecting their transplant, which means that their transplant has failed and they need to get back to hospital. So the question or problem statement is, can we reduce the time spent by clinicians on reading notes for a cohort of patients? So now we would like to limit clinicians' time spent on reviewing these notes. Therefore, we planned to find an ML-driven solution like an NLP model to achieve this. But an NLP model requires annotated data set. And what if we don't have enough annotations? One thing we can do is approach annotation services, but as we all know, clinical annotation services can be pretty costly. And also, clinical annotating clinical data sets is also an operational bottleneck for a lot of organizations. So first, I would like to briefly touch upon what are the main types of NLP annotations and which annotation type was applied in our specific use case. First one is entity annotation, where you annotate each word in a sentence. This type of annotation is one of the most important processes in the generation of chatbot training datasets and other NLP training data. The second type of annotation is entity linking. This is the process of connecting those entities to larger repositories of data about them. It is used to both improve search functions and user experience. And annotators in this entity linking annotation type are asked to connect those entities to larger repositories, or in other words, they're asked to link those labeled entities within a text to a URL that contains more information about that entity. The third one is sentiment annotation. This one is the labeling of emotion, opinion, or sentiment inherent within a body or text. In this category, annotators are given texts to analyze and must choose which label best represent the emotion or opinion within the text. A very simple example would be the analysis of customer reviews. So annotators would read the reviews and label them as positive, neutral, or negative. The fourth type of annotation is text classification. It's also known as the text categorization or document classification. In this, annotators read a body or text of short lines or a paragraph of text, and annotators must analyze the content, discern the subject, intent of the text, and sentiment within it, and classify it based on the predetermined list of categories. So, this is the category of the annotation that we used in our use case, which is text classification. Now, for example, we have 500 annotated notes provided to us by our data experts, which in our case are clinicians, and we need to acquire 1,000 more annotated notes to use these annotated data for an NLP model. Or, in other words, so that we can use this large set of annotations and feed them to our NLP model and further use it for doing more predictive or ML based tasks. So, how can we achieve a bigger set of annotated data by just having a smaller set of annotated notes and hence minimizing overall manual annotation process? So here our main goal is to see how can we make use of annotations or a small set of annotations we have in hand and use it in our favor and create a larger set of annotated notes and further use those annotated data set in NLP or RML models for further predictive tasks. So, to achieve this, we followed a methodology which I'll be going through on a high level basis and elaborate more on each step as we proceed through the slides. So, as our first step, we annotate a small volume of notes or train annotation assistance, small volume of notes to train our annotation assistance model. Now, let's take a step back and explore how we familiarized ourselves with the data that we had in order to proceed with the annotations. Now, we as human annotators read through a good number of these patients' notes and tried to understand the reason why a note is annotated as yes. Yes, meaning this note has diarrhea. Initially, we had a lot of confusing texts that we were not able to understand properly. We made note of all those texts and met with our data experts and hence received guidance from them to understand confusing terms or the confusing note texts that we were not able to understand and which we were not able to annotate. Now, this process made us as human annotators more familiar with the data set and the rules of annotations, meaning what terms or words to look for in a patient's note to annotate that note as yes or no diarrhea for our particular use case. Now, because of this step, when our annotation assistance tool gave us the rules, we were able to check the rules given by the classifier to our rules as whether or not they seem similar, and hence we were more confident of rules given by our annotation assistance tool. In our use case, which is the diarrhea BMT use case, we used decision tree as our annotation assistance model, which gave rules based on the training data set it got or the small handful of annotated notes it got. Then those rules which are derived from annotation assistance model are used to label a larger volume of notes. And in the final step, we feed all the annotations to the NLP model. Now let's dive into more detail on how to achieve a larger annotated set or larger annotated patient notes from a small number of annotated records that we had. Now, in the first step, we annotate a small volume of notes to give as input or as training data set to our decision tree model, which is our annotation assistance tool. But why did we use decision tree as our annotation assistance tool? So, decision tree firstly requires less annotated nodes compared to more complex ML based model. What I mean by that is the more complex ML model is, more training data is needed. And since decision tree is a simple model, it works with less annotated data. And one other important factor as why we used decision tree as an annotation assistance model is because it's very easy to understand what a decision tree is doing compared to other complex model. What I mean is, when a decision tree model is run in your coding interface, it's very easy to understand the rules or the steps that a decision tree is taking. It's very easy to comprehend for a human being to understand what an ML model is doing. Compared to when you run a very complex ML based model, you don't really get the full picture of what's happening in the backend or how did you get a particular result. So this is one of the reason why we decided to go ahead with decision tree and use that as our annotation assistance model. In general, a decision tree is a binary tree that recursively splits the dataset until we are left with pure leaf nodes. And when a set of annotated nodes is given to the decision tree model, it gives annotation rules for positive and negative class. Then the model selects 100% pure leaves from train and evaluation set. Now, one may ask, what are the rules given to you by your annotation assistance tool? So, for a diarrhea BMT use case, if either of these terms, which are present in the slide, if these either of these three terms are present in patient's notes, it is classified, that patient node is classified as true by the model or it is labeled as yes. Else, these if these terms are not present in patient's notes, the note is classified as false or it is labeled as unknown. Now let's go through all of the three terms. The first one is diarrhea res, means diarrhea response, how a patient is responding to their diarrhea symptom. The second one is loperamide, which is an anti-diarrheal medication. The third one is diarrhea episode. This means if this term, diarrhea episode, is present in patient's note, it means that patient was experiencing an episode of diarrhea for that particular day. So these three are the rules that our decision tree was able to come up with the help of the annotated training data set it got initially. So according to the decision tree rules, if any of these three terms are present in a patient note, our annotation assistance model annotates that note as yes, otherwise it annotates that note as unknown. In other words, the decision tree is annotating only pure leaf nodes as yes, as a sure shot yes, else it's going to annotate that patient note as unknown. Now, we used sklearn, which is a machine learning library in Python. This ML library does not let us set the decision threshold directly, but it gives us the access to decision scores that is used to make the prediction. We can select the best score from decision function output and set it as a decision threshold value and consider all those decision score values which are less than this decision threshold as a negative class, and all those decision score values that are greater than this decision threshold value as a positive class. One more important factor in decision tree is its Gini impurity, and it is an important measure used to construct the decision tree, and it's a function that determines how well a decision tree was split. Basically, it helps us to determine which splitter is the best so that we can build a pure decision tree or we'll get pure leaf nodes from a decision tree. Now, Gini impurities values ranges from 0 to 0.5. Now here we have a pictorial representation of the decision tree. So when you run your decision tree model in your Python code interface, the model itself is going to give this nice pictorial representation for you to understand what's happening in the backend and how the data set were split and what are the rules it was split according to. You can also see the Gini impurity value here for each node, for each leaf node. So here for the first term or the first rule here, we see diarrhea res, that term. If that term has a threshold less than the decision tree threshold, which is 0.5 here, if it's less, then it will be classified as a false class, else it will be classified as a true class. Now, in very simple terms, I'll explain this. Imagine a decision tree reading through the patient's notes, and it finds the first term or the rule diarrhea res in a patient note. If it finds it, then that patient note will be classified as true and that note will be labeled as yes. If not, decision tree is going to move forward and see if the second rule is present or the second term, which is loperamide, is present in the patient note. If it is present, that patient note will be classified as true or labeled as yes, else it's going to be classified as false, or it's gonna move further and see if it has more rules. So yes, it has more rules and it's gonna check for the third rule or the third term it has, which is diarrhea episode. Now, if decision tree sees that this term diarrhea episode is present in the patient node, it's going to be classified as true or it will be labeled as yes, else it's going to be classified as false or labeled as unknown. Now, if the decision tree, when it reads through the patient's note, does not come across any of its rules, that is, neither the diarrhea res is present, neither loperamide is present, or neither diarrhea episode is present in that patient note, it's going to classify that patient note as unknown, label it as unknown, or classify that patient note as false. If any of these terms are present or any of the decision tree rules are present in a patient note, it's going to classify that note as true class or label it as yes. So I hope it was a clear explanation of the decision tree here. Now, after we have the rules from annotation assistance model, these rules are applied on new set of 500 nodes with a similar data structure. And the rules derived from decision tree were able to annotate 30% of these nodes, achieving 98% accuracy. And the remaining nodes that are classified as unknown had to be manually annotated. So here in the diagram, as we see, the new set of 500 nodes that we gave to the decision tree model, it classified 30% of these nodes as pure leaf nodes, or it classified these nodes as true class and labeled them as yes, meaning in all of these nodes, decision tree was able to find one of its rules present in them. So it went ahead and labeled those nodes as yes. And if neither of these three terms, the diarrhea res, loperamide, and diarrhea episode, if neither of them were present in the patient notes, it would be classified as an unknown class, as a false class and labeled as unknown. So when we manually annotate each note classified or labeled as unknown, it took us approx 10 minutes, which equates to roughly 3 days of work to annotate each patient notes, which also shows how annotation assistance model helped to minimize manual labor overall. After we have the required set of annotations, we can then feed all the annotated data set to the NLP model, which can further be used to make predictions or perform any ML-based tasks. So here we see all the annotations, that the larger set of annotations that we achieved from our annotations assistance model, and also by manually annotating the unknown class. We fed all those annotated data set to our NLP model, and we received an accuracy of 84%, a precision of 86.7%, and a recall of 68.4%, which is not bad because considering that we just had a very small amount of annotated notes initially, and then annotation assistance tool came into picture, which reduced the manual labor time overall and helped to give us a much more larger set of annotated data. So I'll touch upon the key takeaways from this talk. We created a simple yet efficient model, which is ML driven. And now we can input a different data set with similar data structure to the annotation assistance tool, and it will annotate patients' notes for us as per the rules of the decision tree classifier. So initially, 500 notes were manually annotated and which took human annotators around 10 minutes per record to annotate. And with the introduction of our annotation assistance tool or the decision tree classifier, 1/3 of the new notes were annotated by rules given by the decision tree model, saving us roughly 3 days of manual annotation time. And rest of the 2/3 of notes were classified as unknown. And these 2/3 of notes which were classified as unknown were manually annotated by us. So that was for my presentation, and thank you for listening through it. And please feel free to contact me with your questions. Thank you.